Welcome back to Learn Math by Example. In our previous lesson, we've explored 4 examples about arithmetic sequence and series. In this video, we're going to continue with 4 more examples so that we can cover all the possible scenarios. By the end, you'll be able to solve these kinds of problems with confidence. In the first example, let's evaluate the sum of an arithmetic series given in sigma notation. The sum from k equal to 1 to 15 of 4k minus 3. This notation tells us we're dealing with an arithmetic series. Our first step is to identify the first term, a1. We do this by substituting k equal to 1 into the general term. So a1 is 4 times 1 minus 3, which is equal to 1. Next, we identify the last term, a of n. Here, n is 15, so a of 15 is 4 times 50 minus 3, which will give us 57. The number of terms n is clearly indicated by the upper limit of the sigma notation, which is 15, since it starts at 1. Now, we call the sum formula for an arithmetic series, which is available in your formula booklet. S of n is equal to n over 2 times a1 plus an. Our final step is to substitute these values into the formula. So S15 is equal to 15 over 2 into 1 plus 57. This will give us S15 equal to 435. In example 2, we are given S of n, the sum of the first n terms of an arithmetic series, as 3n squared minus 2n. Our goal is to find the common difference d and the first 3 terms of the series. First, let's find the first term, a1. We know that the sum of the first one term only is simply the first term itself, so a1 is equal to s1. Replacing n by 1 into the formula, we get s1 is equal to 3 times 1 squared minus 2 times 1, which simplifies to 3 times 2, so s1 is 1. Next, we find the sum of the first 2 terms, s2. S2 is equal to 3 times 2 squared minus 2 times 2. That's 3 times 4 minus 4, or 12 minus 4, which gives us 8. With S1 and S2, we can find the second term, A2. Now A2 is S2 minus S1, which is 8 minus 1 equal to 7. So far, we have the first 2 terms, A1 and A2, which are 1 and 7 simultaneously. Now, we can find the common difference d, which is the difference between the consecutive terms. So d is equal to s2 minus s1, which is 7 minus 1 equal to 6. To find the third term, all we have to do is to simply add the common difference to a2. So a3 is equal to a2 plus d, which is 7 plus 6 equal to 13. Or as an alternative way, we can find a3 by using s3. So we could calculate S3 to get 3 times 3 squared minus 2 times 3. That's 3 times 9 minus 6, which gives us 21. So A3 is S3 minus S2, which is 21 minus 8, which gives us 13 again. So this confirms our answer. Therefore, the first 3 terms of this series are 1, 7, and 13. Now, let's work through a problem where we're given the first and its specific later term of an arithmetic sequence, and we need to find the common difference, d, and the sum of a certain number of terms. Our sequence starts with a1 equal to 9, and the 20th term, a20, is equal to 104. We need to find d and the sum of the first 12 terms, as 12. Notice that n is equal to 12 is not the last position, which is 20. Our first step is to find the common difference d. We'll use the general term formula for an arithmetic sequence. an is equal to a1 plus n minus 1 times d. Applying this on a20, we have a20 is equal to a1 plus 20 minus 1 times d. Replacing our given values into the formula, we get 104 is equal to 9 plus 19d. Subtracting 9 from both sides and solving this equation, we get d is equal to 5. Now that we know d is equal to 5, we can proceed to find S12. So let's use our sum formula. Sn is equal to n over 2 into a1 plus an. We first need to find a12. Using the general formula again, a12 is equal to a1 plus 12 minus 1 times d. Replacing the value that we have in the general formula, we get a12 is equal to 64. Finally, we calculate the sum of the first 12 terms as 12. S12 is equal to 12 over 2 into a1 plus a12. Replacing our values, we get S12 is equal to 6 times 9 plus 64. This simplifies to 6 times 73. We get S12 is equal to 438. Next, let's tackle a problem involving an infinite arithmetic series. We have the series 5, 12, 19, and so on. We need to find the smallest integer n such that the sum of the first n terms, Sn, is greater than 1500. First, let's identify the key components of our series. The first term, a1, is 5. The common difference d is the difference between consecutive terms, so 12 minus 5, which is 7. Next, we write down the sum formula for an arithmetic series, which is Sn equal to n over 2 into 2a1 plus n minus 1 times d. This formula is provided in the formula booklet. Now, let's substitute our values. Sn is equal to n over 2 into 2 times 5 plus n minus 1 times 7. Simplifying the expression inside the brackets, we get Sn is equal to n over 2 into 10 plus 7n minus 7. Further simplification gives us Sn is equal to n over 2 into 7n plus 3. Our next step is to set up the inequality as required by the problem. So Sn is greater than 1500. So n over 2 times 7n plus 3 is greater than 1500. Multiplying both sides by 2 to clear the fraction, we get n into 7n plus 3 is greater than 3000. Expand and rearrange the terms to form a quadratic inequality. So we get 7n squared plus 3n minus 3000 is greater than 0. To solve this quadratic inequality, we first need to find the roots of the corresponding quadratic equation. 7n squared plus 3n minus 3 is equal to 0. Using the quadratic formula, we get n is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Replacing our values, a equal to 7, b equal to 3, and c is equal to negative 3000, we get n is equal to negative 3 plus or minus the square root of 3 squared minus 4 times 7 times negative 3000 all over 2 times 7. This simplifies to negative 3 plus or minus the square root of 9 plus 84k divided by 14. So, n is equal to negative 3 plus or minus the square root of 84,009 divided by 14. The square root of 84,009 is approximately 289.84. Therefore, n is approximately negative 3 plus or minus 289.84 divided by 14. Now let's calculate the two possible values of n. n1 is approximately negative 3 minus 289.84 divided by 14, which is negative 20.91. And n2 is approximately negative 3 plus 289.84 divided by 14, which is about 20.49. Since n must represent the number of terms, it must be a positive integer. We also observe that the parabola of the quadratic expression opens upward, as the coefficient of n squared is positive. Therefore, 7n squared plus 3n minus 3000 is greater than 0 when n is greater than 20.49. The smallest integer n that satisfies this condition, consequently, is 21. With this example, our examples come to an end. To get more practice and solidify your understanding, you can visit us at samshub.com. There, you will find free lessons with lots of exercises. If you know anyone who would need help in his homework or support in writing his IA, you can also direct him to our website. The link is in the description below, along with additional resources. Don't forget, discussion is a crucial part of learning. So if you have any questions or comments about this lesson, feel free to leave them below or on the website. Join us for our next lesson, where we'll explore an application on arithmetic sequence and series, in addition to an unpredicted model involving this sequence, which can be used as an internal assessment topic. Thank you for watching and see you next time.